In this video, we are going to introduce what parametric equations are and look at our first example. So we have a definition at the top here that reads, if f of t and g of t are continuous functions on some interval I, then the set of ordered pairs f of t, g of t makes a plane curve. So f and g are our parametric equations. The orientation of a curve is the direction that the curve is traced out in for increasing values of the parameter. So looking at example 1, we want to graph the curve whose parametric equations are given and show orientation. And we also want to find a rectangular equation for the curve. So we have two parametric equations here. We have x of t is equal to t plus 2. And y, I don't have the of t here, but you could think of this as y of t is equal to the negative square root of t. And we have that t must be greater than or equal to 0. So the equations of x and y, those are our parametric equations. And the variable t, the variable that shows up in both of those parametric equations, that is the parameter. So t is our parameter. So we want to graph the curve given by these equations. So I have a table set up here with a column for x, a column for y, and then the ordered pairs x, y. And in the first column, we're going to plug in different values of our parameter t. We have the restriction that t must be greater than or equal to 0. And so we must start with 0. Since we have the restriction that t is greater than or equal to 0, the first t value we plug into the table has to be 0. I'm going to choose to also plug in 1, 4, and 9. Typically, I think it's a good idea to have at least 4 t values in your table, and I am intentionally choosing numbers that are perfect squares so that when I go to compute y and take the negative square roots of those numbers, I'll get nice numbers out of that. You don't have to choose perfect squares. In reality, you could pick any numbers as long as they were greater than or equal to 0, with 0 being the first number you plug in. But I'm just trying to make this easier. I think it's also important that when you plug the values into your table, you go in increasing values of t, because that is going to affect our orientation of the graph. So when I plug 0 into x, I have 0 plus 2, which gives me 2. Plugging 1 into x, 1 plus 2 is equal to 3. 4 plus 2 is equal to 6. And then finally, 9 plus 2 is equal to 11. So we filled out this second column by taking our t values and plugging them into the equation for x. Now plugging our t values into the equation for y, the negative square root of 0 is 0. The negative square root of 1 is negative 1. The negative square root of 4 is negative 2. So I'm just plugging 4 into y. And when I plug 9 into y, we will get out negative 3. In the last column, I'm just going to make a note of the ordered pairs that we found. When t was 0, we got the ordered pair 2, 0. That's from the x value of 2 and the y value of 0. When t was 1, we got the ordered pair 3, negative 1. When t was 4, we get 6 as our x-coordinate and negative 2 as our y-coordinate. And then finally, when t was equal to 9, we get 11 as our x-coordinate and negative 3 as our y-coordinate. So now I'm going to head over to this coordinate system here, and I'm going to plot these points. So the first point we have is the point 2, 0. So I'll plot 2, 0. And then when t is equal to 1, we get the point 3, negative 1. So we have the point 3, negative 1. And then when t is equal to 4, we have the point 6, negative 2. So here's the point 6, negative 2. And then finally, when t is equal to 9, we have the point 11, negative 3. And so there's that point 11, negative 3. And so this graph, when I connect these points, looks like this. And notice I did not stop at 11, negative 3. I could have continued to plug in larger t values. Say I could have plugged in 16 or 25, etc., etc. And so the graph is going to keep on going, and so I'm making sure to put an arrow on that end of the graph. Now we also have to show orientation, and so we do that with arrows within the graph. So our first point was the purple point 2, 0, and then it went to the blue point 3, negative 1. So I'm going to put a little arrow on the graph showing that it went from the purple to the blue, and then from the blue point of 3, negative 1, it went to the green point of 6, negative 2. So I'll put another arrow there. And then from the green point of 6, negative 2, it went to this light blue point of 11, negative 3. So then I'll add another arrow in there. So these red arrows on the graph, what they do is they show orientation. So whenever we graph a parametric equation, we need orientation arrows on the graph showing which way the graph is being traced out in. Again, this last arrow here is not, it's showing orientation as well, this last gray arrow, but mainly that's because t is greater than or equal to 0, and so it's going to continue off in that direction forever. The second thing we want to do in this problem is we want to find a rectangular equation, and so what that means is we must eliminate the parameter. So we want to be able to write this equation, an equation for this graph, but write it without having t in there. A rectangular equation only involves x and y. We want to only have x and y in our equation. So we have the two equations, that x is equal to t plus 2 and that y is equal to the negative square root of t. So I'm going to take one of these equations, it does not matter which one, and I'm going to solve for t. I'm going to take the first equation, x is equal to t plus 2, and I'm going to subtract 2 from both sides to see that t is equal to x minus 2. So now that I know that t is equal to x minus 2, I am going to plug that in to the second equation. So the second equation was y is equal to the negative square root of t. I am going to take the fact that t is equal to x minus 2, and I am going to plug that into this second equation. So the new second equation now, when I replace t, I will have y is equal to the negative square root of x minus 2. So now here we have an equation that only involves x and y. So this is our rectangular equation. And if we were to take our rectangular equation and graph that in the graphing calculator, we would see a graph that looks like what we graphed up here from plotting the points that we got when we were plugging in our parameter of t. So to show you that, I have put into my y equals our rectangular equation of the negative square root of x minus 2, and I'm going to hit graph, and we see exactly what we have plotted here. This starts at the point 2, 0, and then it goes on in the same direction that our graph goes on into. And so since this matches our graph exactly, we do not have to restrict our domain or restrict our range or anything. Later on, we will see examples where we have to put some restrictions on our rectangular equation.